Moving on to Chapter 26, Carbon-Carbon Bond-Forming Reactions. Recall we have seen a couple of reactions where we form carbon-carbon bonds, where we have an acetylide ion, strong nucleophile, will attack a carbon that has halogen on it, standard SN2 type of stuff, to make a carbon-carbon bond. We've seen Grignards and organolithiums and alkyl organolithiums and organocuprates, yes. These organometallic reactions, when you have a carbonyl, one of these organometallic reagents, you can form a carbon-carbon bond. And we've also seen aldol type reactions with enolates, where we can make a carbanion and attack a carbonyl. Okay, there's another class of reaction that uses some pretty decent inorganic catalysts, some heavy metal catalysts such as palladium. And in general, let's look at some general information about these reactions. Just get some terminology down, know what it means. I'm not going to really test you on this, but just some general terminology. When you have an atom from a transition metal, you can bond other atoms or groups of atoms to it, such as chloride ion, ammonia, triphenylphosphine, phosphorus with 3 phenyl groups on it. These are called ligands. These are atoms bonded to a metal, and we call them ligands. And normally when we consider ligands, we are of the thinking that the bonding pair of electrons, both electrons come from the ligand. So this ammonia, when it bonds to a metal like a palladium, both electrons here come from the nitrogen to form a covalent bond with the metal. Recall, this is not shocking. Remember up here when we have the acetylide, we could have a sodium or a lithium, and also with our organometallic reagents, we could draw it as a single bond between the carbon and the lithium, or we could draw it as a carbanion because it reacts as carbanions. Either way, if you drew it as a single bond, both electrons would come from the carbon up here. Here, both electrons come from the ligand when bonded to the metal. Now, when you have these complexes with these palladium catalysts, you can get oxidative addition, where you've got the palladium with 2 ligands on it. If you add just Rx, you will find that the R group and the X group, this bond breaks, and they each get bonded to that palladium. You can also get reductive elimination, where you have our 2 ligands on a palladium, R and H are on there, and these 2 go away. They break off of the palladium and bond together in the process. So oxidative addition, you add a bond, or you add 2 groups to the metal. Reductive elimination, you get rid of 2 groups that are on that metal. So the first reaction we will look at is the Suzuki reaction. It is palladium catalyzed, and usually the catalyst, look at this, it's a palladium with 4 triphenylphosphines on it. Now way up here was our triphenylphosphine group, and look how big that is. 3 phenyl rings on a phosphorus. That's a rather decent sized molecule. Imagine 4 of those triphenylphosphines on a palladium. That's 12 phenyl rings and 4 phosphorus on a palladium. That's a monster. That's huge. All right. But what this catalyst does, it'll couple R'(X) organic halides, alkyl halides, with RBY2, these organoborane compounds, in the presence of base, such as sodium hydroxide or sodium methoxide. And the general reaction is like this. You take R'(X), our halide, our organoborane compound, put in your catalyst in NaOH, and you will bond together the R' and the R, make a carbon-carbon bond, and end up with this stuff left over. And truthfully, we don't worry about this stuff. It's that carbon-carbon bond that we're after. You know, carbon-carbon, making carbon-carbon bonds is important because as we go through all these reactions, they are all named after the people that came up with them. All right. And what Suzuki found is these reactions are most useful for vinyl and aryl halides. So normal alkyl halides, alkanes aren't going to work, but if you have a vinyl halide or an aryl halide, these will work really well. So for example, if you take bromobenzene here, and then here's our borane molecule, and when you look back, you noted that on the previous page, the borane was bonded to two Y groups plus our R prime. This is the R group. This is the R group. This is the Y group. And we like to keep it together as one beast there. It tends to work better. So what this will do, whenever you see this reaction, you see, okay, alkyl or aryl bromide here, and you see this boron here with this group on there, you know that this group on here will be attached to this group here. And that's what happens. Here is our chain with a double bond, and then the carbon of the double bond was bonded to the boron. Now that carbon of the double bond is bonded to the carbon of the benzene ring. And that's the way it works. And the nice thing about that, you'll note the double bond stays. You still have the phenyl ring, you still have the double bond there. You didn't get rid of those two groups. You just attached them together. Note here, another case where we have phenyl ring and here's the bromine and we've got a vinyl group there. Here is our beast again, our borane compound. We know that this is the R group, so we're going to attach this carbon here that was bonded to boron will now be bonded to what this bromine was bonded to, bonded right here. And look at that, we've got a phenyl ring, we've got a conjugated diene. Perhaps we feel like doing a little diazolder. Maybe we don't. It's up to you. Cool. And note these reactions are stereospecific. So if our vinyl halide here is cis, and this is trans, we'll find out this is always trans, then this will keep its cis stereochemistry and the trans stereochemistry. So we can tell in this reaction this is concerted, this and this add together, and there's not going to be bonds broken until bonds are made, so that it keeps the arrangement. So, well, how do we make this beast here? How do we make the boranes? One reason I go over this is because it's really reviewing some organic 1 material. Recall hydroboration oxidation, where we added a BH3 to a double bond? We're going to do a similar thing. Remember, with hydroboration oxidation, we added BH3 to the double bond, anti-Markovnikov style, and then oxidize the borane off. Here we're going to add the borane to the molecule, but we're not going to oxidize it off. So, just like with hydroboration oxidation, this is syn addition of HB in the anti-Markovnikov way. Syn addition, anti-Markovnikov, just like hydroboration. We're going to start with this alkyne, RC triple bond CH, and then if you add this borane, here's our two Y groups on here connected together, boron and the hydrogen here, this borane, you're going to see you get this beast here. This boron bonds to this carbon, the terminal carbon, the hydrogen bonds to this carbon because anti-Markovnikov, the hydrogen goes on the carbon with fewer hydrogens. Boron's going to add to this carbon here, and you get this beast here all the time, syn addition. So because it's syn, this will be trans. Our vinyl borane will be in this trans configuration. Okay. And we can make this, the other piece of it, or another way to make these is to take a lithium, say, lithium on a benzene ring, an organometallic, with this boron with 3 methoxy groups on it here. And then you can get the benzene ring on the boron with 2 methoxy groups. That's how, instead of a double bond here, a vinyl group, you can put another phenyl ring here. All right. Here is the mechanism for this process. Again, I'm not going to test you on the mechanism. I just want you to see what happens here. So it's not something like crazy, I don't know, it just works. Well, this is how it works. You take our 4 triphenyl phosphenes on a palladium. We call that tetrakis triphenyl phosphine palladium. And then 2 of those triphenyl phosphenes leave to make bis triphenyl phosphine. It's not ditriphenyl phosphine, it's bis triphenyl phosphine on the palladium. So this is our catalyst after 2 of those groups leave. Then our R'(X) adds oxidative addition. Our hydroxide plus our borane compound here is going to, this hydroxide, put a negative charge on here when hydroxide adds, which makes this guy really say, you know what, I want to get on that palladium instead. So it gets on the palladium and the halogen leaves to go here, and then you get the reductive elimination as these 2 bond together to make R'(R), and we get our catalyst back again. All right, don't spend much time looking over that mechanism. That's just showing you how it occurs. More importantly is to recognize that, okay, this is a Suzuki reaction. I can see those 2 reactants, and so I know the product. So here we go. Here is this alkyne, and all right, here's this borane here, the boron with the hydrogen on it, and we're going to add that first, and then add this vinyl bromide second. So we know, oh, okay, alkyne, this boron with these 2 Y groups. Note, how do you know it's not hydroboration oxidation? Because this is not BH3, and there's no oxidation, there's no H2O2. So we know, okay, this is Suzuki reaction. So we know this boron's going to attach to this carbon, the hydrogen's going to attach to this carbon here to make the double bond, this trans double bond. And then the carbon that contained the bromine is going to be attached to this carbon here with a single bond. We know this is trans, we see this is cis. So we're going to end up with our phenyl ring with our cis double bond, and then into this trans compound that was with the boron. Okay, ooh, nice lot of conjugation there, and that is a driving force of these reactions. You end up with conjugated systems which are stable. Well, should we look at another one of these reactions? The answer is, of course, heck yeah. The Heck reaction. Here we're going to take a vinyl or aryl halide with an alkene to make our conjugated products. Let's look at how this works. R'(X), where R' is going to be a vinyl or aryl group. We need conjugation here. This has to conjugate with this in order to get the reaction to go. Whereas our halide is going to be bromide or iodide. And then our vinyl group is going to have this Z on it, where Z is going to be either a phenyl ring or a carboxyl group here, or nitrile, something along those lines. Note our catalyst. It's a palladium catalyst, but instead of triphenyl phosphines, we got a bunch of stuff in here. It's palladium with 2 acetate groups on there, so this is palladium 2 acetate with a phosphorus with 3 orthotolulyl groups. So that means instead of a triphenyl phosphine, it's a triorthotolulyl phosphine. And orthotolulyl just means that it's a toluene, which is a methylbenzene, and the methyl group is ortho to the phosphorus. Plus this triethylamine, which I bet does not smell good. All right, and when this occurs, this R' will get bonded to the Z, and it will be trans. It is always going to be in a trans configuration. Recall R prime is vinyl or aryl, so we should get conjugation. Here's an example of it right here. Here's R prime X, this phenyl bromide. Here is our double bond Z group here, and we know, okay, this is pretty straightforward. I see phenyl bromide, I see Z, I see this mixture, this catalyst here, this mixture here. You're just saying, okay, this is Heck reaction. All I have to do is attach that phenyl ring to this carbon trans. That's it, phenyl ring to that carbon trans. There is the product. And we can think about this retrosynthetically. If you say, okay, I need to make this big monster molecule here, and you say, oh, wait a minute, there's a conjugated double bonds, two double bonds conjugated together. I know I can make, oh, and look, here is this electron withdrawing group here, this acetate group. I know that I can just form this bond using a Heck reaction. If I just had this piece of the molecule with the bromine on there, and then just this piece of the molecule, all I have to do is take those two pieces, throw in this catalyst system, and there I can make that bond. So at the beginning of the semester, when we were looking at Diels-Alder reactions, when we needed a conjugated diene, probably the big question was, well, how do I make conjugated dienes? We found a couple of ways so far. Here's another way. A Heck reaction will make this conjugated diene for you. Okay. In the next video, we will continue on with another type of reaction, carbenes.